session. And today, a good news for you. And today we'll have a little bit of math, but yeah, just keep it simple. So so just be relaxed. And we first go through some concepts using whiteboard. Then we show some code, and probably we can do just to understand the concept, and by writing Python code, and we can if you're interested in the homework, yeah, I can leave some exercise and homework for you. Today's topic is about the Peterson commitment. Sorry, Peterson. Sorry. Peterson commitment. Okay. First of all, let's review the protocol that we talked last Friday. If you for those who missed the last Friday's session, it's okay. So you can read the articles I wrote. I put the link in the DC channel, so you can just check it out. And so first of all, the first topic of today's session is just review the Schnorr protocol, because Schnorr protocol is simple, but it's a start point of our whole journey. Schnorr protocol. Okay, Schnorr protocol is simple. It's a 3 rounds protocol. So Schnorr protocol is one of the famous family protocols called Sigma protocol. Sigma protocols. Protocol family. Can I see that? Why Sigma? Because Sigma kind of just like 3 round. So it looks like a 3 round interaction. So we call the Schnorr protocol-like protocols, we call them Sigma protocols. So already we all have 3 rounds. We have the Alice as the prover and Bob as the verifier. Okay, prover has a secret key, and we used some notation last Friday. We use a square brackets, put the SK inside, we got a public key, right? Public key. But we didn't say much about what the square bracket is. So, but today we will explain more about square bracket. Okay, to make sure that everything underlines the solid, and we can write some code for them. But the verifier cannot access to the security key, also the private key. But the verifier can have the public key to verify the identity of prover, Alice. So in the first round, the prover generate a R randomness. It's a randomness. Toss a Bitcoin, get a random R, and compute a commitment of R, capital R. We put R into a box. The box. Okay, right now the black box is, we just view it as the abstract concept. So in the first round, prover sends R, capital R, it's a black box, to verifier. Verifier cannot get the small r out of it because it's black box, okay, it's locked. And then the verifier replies with a challenge. So challenges is also a randomness. Okay, like we toss a coin, get random C from. At the last step, prover will calculate Z as AR plus C times SK. Sorry, K, okay, PK, okay. I send Z to verifier. So what Z is, Z can be just can be seen as a encrypt SK, and R can be we can see that as a one-time encryption key. It's a symmetric encryption. Now the verifier can verify, homomorphically about this equation to make sure that actually, okay, the prover has the SK. So the equation used by the verifier is like this. Okay, R plus C times PK. Okay, here we, okay. All right, it's the process of the Schnorr protocol, right? Okay, it's simple. Okay. And let me check the outline. If you have any question, please stop me, okay? Okay. So then we prove that actually the Schnorr protocol is both sound and zero knowledge, right? By using the simulation idea, right? But it's something I missed last Friday, that actually we have to pay attention to an important point of soundness. Actually, we have two different soundness concepts. The first one is soundness. Soundness, okay, saying that, okay, any dishonest prover cannot pass the verification. The soundness thing. And another one is a knowledge soundness. Knowledge soundness. Okay. Knowledge soundness is stronger than soundness. Knowledge soundness saying that, okay, there exists an extractor which can extract the private key from prover only in simulated world. Okay, that's his knowledge soundness that implies. So last Friday we just I talked a lot about knowledge soundness, and because knowledge soundness is stronger than stronger than soundness, so if we prove the knowledge soundness, then we prove the soundness. So what are differences between, okay, besides the stronger one is stronger than another? still, the intuition behind the differences is that soundness actually prove that existence of private key. Soundness saying that, okay, exists a SK such that SK square brackets equals to PK, right? Because PK is public, it's public input or public seen by everybody. So sound is proving that, okay, the PK is not is a randomly generated, actually. The PK, there is some SK somewhere, but probably we don't know, is associated with the PK that we can see. Okay, the sound is saying that existence of knowledge, so this problem is solvable. Okay. But knowledge soundness is stronger than soundness. Knowledge soundness saying that, okay, exists an algorithm extractor, and we can use the extractor to extract the SK. So the extraction of the SK implies the existence of SK, for sure. Right?
Extractor an algorithm extractor.
Yeah, extractor is algorithm. It's programmable. We can use Python, Java, C++ to implement extractor. It's algorithm. But in soundness, the normal, the regular soundness, the statement saying, okay, there exists a private key. Okay, but in many realistic or practical systems, yeah, if we as a protocol designer, we have to pay attention to differences between those, because sometimes we need to, for example, in Shillong protocol, soundness is not enough. Why? Probably the prover is the intermediary. So how to say that? Okay, the prover does not has any private key. It's just a middleman. It's not enough. For example, for the digital signature, we strongly require that the prover has knowledge, own knowledge. Okay, the sound is not enough. Okay, so we have to pay attention to what we want. Either is knowledge soundness or soundness, kind of tricky. So if we design protocol, we have to be very cautious about that. So that's the reason why we can see the two different concepts, snark and snark. Snark, yeah, we always see the snarks, right? Snark, saying that actually we prove the knowledge soundness of that proving system, but for snark we only prove the soundness. So for reason of safety and security, we should always use snark instead of snark, unless you know what you are doing. Okay. So use snark always, unless you know the differences. Okay. So snark is a proof of knowledge. Okay. It's a knowledge proof. Knowledge proof saying that, okay, we can, yeah, not only the knowledge exists, but also we can drag the knowledge. Okay. Okay, this is the first part of just a review what we talking about last Friday. So, any question about this part? No? Okay, good. So I think next last Friday I didn't say too much about speak too much about the square bracket, right? Right now, just trying to just understand what the square bracket is. Okay. The commitment. Okay. Last Friday I mentioned that we have generally have two approaches to construct a square bracket, a box, construct a box. The first one is okay. There's a concept called the finite field. Finite field. How many of you know finite field? Please use your hands. 1, 2, 3, 4. Okay. Finite field.
Can you write it for me?
Can you write it?
Yeah. Okay. Thank you. Yeah. Finite. Finite field. We generally have a different, for example, the probably is FQ and prime, sorry. The prime field or extension field. So for prime field, we probably will use the notation of P, and the P is a prime. It's a large, very large, huge prime. And extension field will have the construction P to K. Okay, currently we're just focusing on the prime field, which is very common used in ZK stars. Okay, in the finite field, there are many very beautiful algebraic structures or patterns inside. We will utilize those patterns to build our snarks and proving system. But I think it's very important as a basic concept. You know, we have to understand that completely about. Okay, but focusing on the prime field kind of much easier than extension field to understand. So what prime field is? Prime field is Fp equals to a set from 0, 1, 2, 3, blah blah, to p minus 1. A set. Okay. Each element is an integer, and P is prime. Okay, P must be prime. Okay. Now, what the black box is? Okay, we introduce another notation that Fp star is the multiplicative group of Fp. So Fp star equals to 1, 2, 3, all the way to p minus 1. Or we can see it as a p. We just remove 0 from a p, we got a p star. Okay. It looks simple. It looks very simple, but a p star, it proves that. Turns out there is a very beautiful structure in it, and we'll utilize the feature of a p star to build a square bracket. Okay. There's a basic concept of p star is that this set is called it's a, because we call it multiplicative group. It's a cyclic group. It's a cyclic group. it implies that a P star can be oh my god. Let's use another alpha. So a P star can be constructed by an alpha. Here, alpha is one of a special element in the set. Alpha is in the set of P star. And we can construct the set just using alpha. Alpha to 1, alpha square, alpha cube, blah, 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 to alpha P minus 1. I think P minus 1, yeah, P minus 2, I think. Yes.
Why 2?
Yeah, P minus 2. Because a P star, we have P minus 1, the order of this set, or the size of the set, is P minus 1. So we use alpha repeatedly do the multiplication by itself. We will eventually get the FP star. So that means that for any beta in a P star, will always have, or there exists an use K, for example. There always exists K such that alpha to K equals to beta. Always. Okay, the theorem. It's theorem. Okay. It's easier to prove if we accept that fact. Okay. Yeah, we will check it. Using my computer just after the whiteboard part. Okay. Trust me. This holds. Okay, always.
And the fourth line is equal FB divided by Z.
Okay, it's a set minus. Set minus. We have a set. I just remove these elements out of the set. We got a new set. Okay.
Do we remove the minus just so if you want to multiply, it's not 0?
Yeah, if some element multiplied by 0 be 0, yeah, it's collapse.
So you
Yeah.
just remove it.
Yeah, remove it. Yes.
And alpha is an element in the.
Alpha. Okay, all right. Alpha is primitive. It's a jargon. It's a math jargon. Primitive element. Or some books they call alpha as a generator of a group, of a static cyclic group. Okay, it's a math jargon, but we just remember that it's easy to remember. Okay. In finite field theory, it's called primitive element. So saying that we can get all elements of P star just by use just one alpha. Okay. It turns out there's many alpha here inside. It's a set fact. It's a fact. It's a fun fact. Okay, alpha is special. Okay, for sure, but we have multiple choices. And for different alpha, we will have different order of this set, because in the mathematical concept of set, we have no order about the elements. But using alpha, if we specify one generator or one primitive element, for example, okay, this alpha, we use this alpha to generate the whole set, we will have the order, just by saying that alpha to 0, alpha to 1, alpha square, okay, blah blah, we will have one list of.
Can Can you give an example? Like where alpha, the set of alpha is different to FP star, for example?
Okay, you want to see the example? Okay, let me use the computer
You
to.
don't have to, just if you think it makes sense. Maybe it doesn't make sense.
Okay, just you use the whiteboard. So let me try. For example, the F7. Okay, F7. Seven is a prime. So 7 star. Okay, I have 1, 2, 3, 4, 5, 6. I randomly guess if 2 is the element. If 2 is not, I will try 3. I don't know. It's I just came up with this example, so let me try. Okay.
One important thing is that you're operating on a modular field, so you're always going.
Tri-modular fields, or
Yes, so you're always going like from when you reach to p minus 1, then you go to 0 again. So that's why you can generate
Okay.
the elements from the
So,
from 1.
yeah. If for example, if 2 to 3 equals to 8, right? We have do a modulus operation by 7, so we'll get a 1 again. So now because 2, 1, 2, 3, 2, 3, 2 square, 2 cube, we get 1, 2, 4, 1. Okay. 2 is not a primitive element. Why? Because 4 is get a 2, right? We cannot get 3 from as if we treat the 2 as the primitive element. Okay, we failed to construct the whole set, right? So let just me try the 3. 3. I got 2, 3, 3. 6. Yeah, great.
And it's 4.
4, right? Am I right?
Yes.
5. 1. Yeah. We got all elements of F7 star, F7 star. So yes, 3 is the primitive element.
2 is not a primitive element because 2 to the power of 5 is
4.
Actually,
why is 2 not a primitive element?
yeah, because when we keep raising the power of 2, we can't get all the elements of the field. Like we can multiply the 2 as many times as possible, but it will just repeat 1 to 4, 1 to 4, 1 to 4.
Okay.
We can't get 5, 6.
Large P. So now we define the square bracket R, okay. Now we can put alpha R equals to bracket R. Just because we cannot compute, okay. Here is or we can say in a logarithmic form that K equals to log alpha gamma. Okay, this problem is called the discrete log hard problem. Discrete log problem. But here is a reminder that discrete log problem is related to the factorization problem, which probably it can be solved by a quantum computer in the future. But we don't have to worry right now. Okay. Any question about this part? So if you put R into a square bracket, actually we can use alpha to R, or put R onto the exponent of this expression. So R can be just to choose one primitive element from P star as the public parameter. We just use that public parameter. Okay, so now we can use this definition to rewrite this protocol, right? To replace every square bracket box with the exponentiation operation. All right, just stop here for 2 minutes. And then we will we'll to the Peterson equivalent. Sorry.
Can we take some time to talk about this?
Yes, for sure. Okay. 啊？就说 OK， 因为在这里面，你如果这个属于它的话，它一定是阿尔法的某一个次方生成出来的。对，所以说我们一定存在这个 k。但我们能算出来这个 k， 你要算就得算这个 log 去 k。
意思是这个 k 在这个输出例上，这个 k 指的是能找到的一个乘法，就是循环群的一个值。
对，因为这个必然这个就是任何一个有限域里都有一个循环群。
那这个 k 的这个解决范围是所有的自然数？
不是，这个 k 的范围就在0到 p 减2之间。
然后它不需要循环。
需要循环，那是因为你这个数很大，因为你这个 p 很大的话，你肯定不能挨个找啊。如果这个 p 是一个1000 bit 那么大的，你可能不能枚举，对吧？你没有那么高算力，所以说你就得找到一种算法去快速的算到是大概是个什么样的 k， 这阿尔法的 k 次方恰好就等于伽马。
伽马是指哪个？
伽马就是我们任给一个，对，任给一个伽马。for 的伽马 ，for 的伽马，对。Right.
So first one, for this case, like for prime field, this one I understand it. For something there's something that I'm trying to understand. So the alpha can be like any kind number, but
okay, alpha is inside. We choose some alpha, some elements that are different, are special.
Okay, so for example, for this one, the f prime 7, we can only choose from 1 to 6 in this set.
Yeah, yes. So 7 is small. It's an example. Yeah, it's very simple.
For the k is more like the index of this one.
Yeah, yes.
So technically, k can be like going on forever. Isn't it like it's just 0, 1, 2, 3, blah blah, something like that?
Yeah.
And then for the result of the how can I call this one, like the alpha, let's say like this one is 2, right? So alpha is 2. And
okay.
Then, like 2 of the 0 mean like we need to get. I'm trying to get it.
Okay, 2 is not primitive. Please remember that. But 3 is. And 3 is primitive. So 3 is the alpha, but 2 is not.
Is alpha always unique in the set?
Okay, there are multiple choices. Actually, here probably we have 2 or 3. Yeah, because it's small. Yeah.
I see. So what about the result of this one?
Sorry?
how can this be resolved like 1, 2, or 4, something like that? How can this one resolve?
Result?
I mean, like I understand that the result of this.
What do you mean by result?
Like the generator, for example, we put
Okay.
alpha, we put k, and then we get this number.
Oh,
Like,
yeah. So are you asking that what's the specialty of the two?
Okay.
Right? Is that your question?
I'm trying to figure out that why this one is resolved.
Okay.
Shows 1 or 2 or 4, something like that.
Okay, because 2 to 0 is 1, because any number to 0 is 1.
This one. Okay.
Yeah.
That is power.
Yeah, power. Yeah.
Okay.
2 to 3 is 8. 8 mode. Modulus 7 equals to 1.
Ah, oh, this is modulus.
Yeah, modulus.
Always
Yeah,
modulus.
yes.
Okay.
Always modulus. Yeah, yes. Yes.
primitive，这个 R is no primitive，这样指的是什么意思
It's not primitive. 它不是一个 primitive element.
不是一个素数。
对。
我好奇它为什么一定要在素数上找？
不一定非要素数，只是素数比较
方便，
就比较快。对，一般是说找五个左右，不管它有多大，找5个左右一定能找到。
各种方法。
对，不管这不有多大，这是一个经验，对，这有一个算法，经验算法。
实际上，那我理解这个 K 实际上是反正就是它在 mode 之后可以，就是它可以任意数，但是因为它 mode 之后，它又可以回到原来这些。
Yes.
就实际上它这个数是什么都无所谓，反正最后 mode 一下，它其实就在这个域。
Yes.
明白。
Okay. Great.
但我还是不理解为什么一定要素数。就是
OK， 不一定素数，有些不是素数。
So I think these two between the alpha, if we put alpha to 2 equal to 2 and alpha equals to 3, this will have different results, right?
Yeah. Okay. 2 is not an element. So here we emphasize alpha must be a primitive element. So R2 is not a alpha. But 2 actually, I think in the future probably we could talk about 2 is the generator of a subgroup. To generate 1, 2, 4, 1, 2, 4 is a subgroup of this group.
Yeah, because this one is
over
and over again.
Yeah.
The
circle in the small circle, right? In small circle, it's a bigger circle.
This one is a little bit bigger. But eventually it will be loop.
Yes. Every element will loop, but the period.
Okay, the
A little bit different.
would be
Always the factor of p minus 1.
okay.
For example, 7 minus 1 equals 6. 6 will have 1, 2, 3, 6 for different factors. So for each element, it will have its own period. Yeah, cycle period. For 1, just period is 1, and 2 is 4, 3 is 6. You can test every element of that. And the different periods will form different patterns. Yeah, it's a beautiful, very beautiful structure in algebra. Yeah. Interesting, right?
Yeah, I mean, just see mod 7, and I just know a little bit of like the modular stuff. Okay, I think it starts making sense.
Okay.
Because at first I wondered radical is 1 and radical is 2, and I forgot.
Sorry, I forgot that. To mention that the modulus. Yeah. Sorry.
Not false.
Yes.
Okay, so for the last part, this one I can catch up.
Okay.
Yeah. Like I'm not really sure that.
Okay, let's continue. Okay.
And maybe also say
All right. Okay. May I have your attention? Let's move on to the section 3. Okay, Peterson commitment. So Peterson commitment will have a slightly different definition with the commitment here, square bracket. So Peterson commitment. So if we commit a K as the secret, and along with a blinder R.
Hello?
Blinder.
What's blinder?
I will explain. Sorry, blinder. The blinder is seems like we add more randomness to the commitment to make sure the commitment, from by others saying that okay, it's a random, look like the randomness. Okay, here in Shinobu, in this one, if we commit, sorry, let's do this. If we commit A and then commits B, so if A equals to B, that square bracket A must equal to square bracket B, right? Okay, if we put A into a square bracket, actually it leaks some information. Even we don't know if we got two commitments, even we cannot extract A and B from or B from boxes, but because the two boxes are equal, we still get information, get knowledge that okay, the secret put into two boxes actually they are equal with each other. So we got knowledge. So it's not their knowledge. Right. So here I use Peterson commitment. We'll add an additional blinder, randomness, with K. So to make it, more random, looks like random. So such that if we commit A as RA and A RA prime, if the randomness to element RA and RA prime are different, the final commitments are different, even the same secret in the two boxes. Okay, the definition is that, okay, let me use the multiplicative explanation operation to define that, okay? GK times HR. And the G is a primitive element, is a generator of a P star. And H is randomly chosen from a P star, such that H is not equal to G. So there are two different bases. And we define the commitment as in this form, okay? G2K times H2R. And G is the generator of a P star. H is another element from F7 star that is different from 3. So, but okay, don't use that example because this field is too small. Imagine that the P is very, very large, 1,000 space long. So we put more randomness into the commitments such that we can build zero knowledge protocol to perfectly protect our privacy. Okay. All right. Let's upgrade this protocol into a more privacy, friendly protocol. Okay. We have prover and a verifier. The prover has the secret, like by just using K, K as a knowledge. And the prover, the verifier has the capital K as the complement of small k with the randomness RK. So verifier get the capital K as the complement of small k, okay? Now, the prover is going to prove the knowledge of small k. Okay. Okay, the protocol is very similar with that. Okay, first of all, in the first step, the prover will generate two randomnesses. Row and the row R. From P. Sorry. We just got two randomness and a commit R, which is a committed to randomness. Row. Okay. How to say it in English? Semicolon? Semicolon. Okay, yes. Row and semicolon row R. Okay, remember that, okay, the element before that is the secret that we want to commit. And the value after the semicolon is kind of randomness to protect this element, okay. So in the first step, the prover sends R, capital R, is a committed randomness to the verifier. So verifier does the same thing as the step in the Schnell protocol, simple Schnell protocol. It's a C, is randomness to challenge the prover. And then, okay. The third step is that, okay, the prover will calculate two encrypted message. One is Z equals to row plus C times K, and the Z R equals to row R plus C times RK, and send both of them to verifier. And now verifier trying to verify if the two values are correct or not. Okay, here's the equations to verify. Okay. R plus C times K. Okay. It's the equation. This is the equation. It looks very similar to this one. So I just expand the definition of capital R and capital K to prove the completeness of the protocol. The completeness protocol. A completeness saying that any honest prover always get accepted by the protocol. R. Here's the definition of R. rho semicolon r rho r plus 3 times small k and rk, and oops, the box still has the additive homomorphic property, so we can put the factor into the box. Rho r plus c times k, c times rk, and still, okay, they are additive homomorphic, so we can add the first element, both the second element, add them together. So rho plus c times k, semicolon, rho r plus c times rk. Okay, the left hand side of this equation, okay, just expand the z and zr, we got exactly the right hand side of this equation. Okay, I just finished the proof of completeness. Okay, let's stop here for 2 or 3 minutes to. You can compare the different version of Schnorr protocol and say what happened in this version. And trying to understand, okay, the looks like, looks like, but something different. Okay, let me emphasize. So this zero knowledge proof is proof of what? Prover has a knowledge. Species denoted by small k. Okay, it's proving. Okay, it's a proof of knowledge. It's a proof of knowledge. Let me use a red pen. Proof of knowledge. Knowledge, aka the small k, small k. So that's okay.
Yeah, just a quick question. So basically, the Peterson commitment scheme further protects the prover.
Yes. Enhance the prover. Yeah.
Enhances the zero knowledge.
Yes. Yeah.
But other than that, it's basically the same.
Yeah.
So I guess my question would be, could we, like, now in Peterson commitment we use finite fields for, right?
Okay, yeah, in practice we use elliptic curve group instead of multiplicative group, right? Why? Because it's not efficient, but it's easier to understand. So in many even nowadays there's many academic papers they use such notations. It's called multiplicative notations to describe the group operation. But in blockchain crypto, we didn't use that. We get used to the elliptic curve group. But some cryptographer complain that, okay, we should use this one because it's legitimate.
So can you quickly elaborate on the difference between elliptic curves and or I mean?
Okay, it looks same. It looks same. It's just same. Elliptic curve more efficient. It's we just use 256 bits long finite field. We can build a stronger security. But we use multiplicative group. We have to use a very large finite field to ensure security is enough. Okay.
the relation between H and G should not be known.
Yeah. Should we? Oh, yeah, yes.
Yeah, like if the relation is known, then anyone can decrypt it.
Yeah, yes. Yes, I will explain that. Yeah, as Alok mentioned, there is a very important, there's a common vulnerability of the scheme. Is here how H is chosen. Chosen, right? Okay, it's a typo. Huh. Yeah. So how H is chosen? Okay, let me. So because H is from IP star, right? H is from IP star, so there we can have the. Where is the? Okay. So let me just use the black pen tool. So because H from P star, so then there exists a, for example, LKP, U, such that H equals to G to U, right? So simple calculation, okay, simple arithmetic. If the prover knows U, so we can just expand the definition, okay. A plus U times RA, right? B plus U times RB. If the two elements are equal with each other, then we can have A plus U times RA equals to B plus U times RB. Then we can solve the RB equals to A minus B plus U times RA over U. So we can calculate RB. So the prover will have the ability, the power to commit two different secrets into one commitment. Okay, what would happen? The prover can literally commit any security into one specific commitment. Okay, for example, Charlie, a third people have a public key there. Okay. The prover can commit the same commitment to the Charlie's public key, such that to impersonate Charlie. Okay. So so the U is like a secret, is a toxic waste, some people say. Or U is called, in academic jargon, it's called the trapdoor. Trapdoor. The U is trapdoor. First of all, we can use a trapdoor to build a simulation, to build a simulated world. In a simulated world, the simulator or instructor can get access to trapdoor, such that to cheat, they are how to say in English? The other side, yeah. Opponent, opposite, or
enemy or
okay, no worry. Okay, it's called a trapdoor. It can be used also aside of that's different from time rewinding or time traveling. Last Friday we talked about trapdoor is another technique we can use to build a simulation world to prove their knowledge and knowledge soundness. So, okay, this point is very important. So, if prover knows U, it will break one important property of commitment scheme. So for every commitment scheme, we generally have two very important properties. Just like for any protocol, we have three very important properties: completeness, soundness, or knowledge soundness, and zero knowledge. The three properties are very, very important. And for any commitment scheme, aside from Peterson commitment, actually for many, almost all commitment scheme, we require two important properties. It's called we don't have space. Okay, here. It's called hiding. The second is the binding. The hiding said that, okay, any adversary cannot extract the secret from a commitment, hide. The binding said that the committer, anyone who commit, okay, cannot commit two different values into one commitment. So different values always imply two different commitments. It's called binding. Binding saying that, okay, the secret value is one-to-one bind with commitment. We cannot make, is two different values committed to same commitment. Okay, binding says that, okay, no 2-to-1 mapping, just the one-to-one mapping. Okay, binding. So if prover knows U, he breaks binding property. So for any commitment scheme, including polynomial commitment scheme, we have to pay much attention to the hiding and binding property. Or we have to inspect any security assumptions there. So if we broke that assumptions or not, we don't know. We have to pay more attention to that. Okay. So a design okay. I think in the past 4 years, so I saw at least 4 reports, vulnerability reports. Okay, just the similar vulnerabilities here, and some developer just blindly, just generate the U and put it in the code, and now everybody can see that U was U is, and it was easily to break that protocol. So then the problem is that how can we generate the U safely in secure way? How? There are 2 ways. So the first one is we direct generate the U by some trusted party. Okay, if I trust somebody, just I ask them for H, okay. But it's dangerous, right? We don't want the trusted third party. The second way is that, okay, we can generate H by some method that is transparent. So it's called a transparent setup. Let me try to write here. Transparent setup. Transparent setup. How? So we use hash function. So okay, the jargon is the hash to point. You can Google that keyword. You can get a lot of papers to teach you how to do transparent setup for the Peterson commitment. The hash point, the idea is that we hash a string. It get a number, then from the number, we look at the nearest little curve point and choose that point as the h. And if someone wants to know that, okay, what the relationship between h and the generator g, okay, he must solve the discrete log problem. Okay, so here we don't want to get too deep into the hash point. Okay, just okay, show you the keyword. Just Google that keyword, you will get a lot. Okay.
So in the Schnorr's identification protocol, we're using random, like we use like the angel for randomness, right?
Okay, that's it's a non-interactive part. Non-interactive Schnorr protocol is a orthogonal problem. Okay.
And I guess my point is just like there we can also get verifiable randomness, right?
Verifiable randomness, yeah.
Yeah. So if I understand correctly, here with h to determine h, like you was just talking about two options. One option was to trust a third party. Why don't we have something similar like verifiable randomness?
Okay, I think the transparent setup looks like the random oracle we used to make in non-interaction. Yeah, it's very similar, right? And this string is a publicly known string. And this is called nothing up my sleeves. It's kind of a cryptographic jargon, saying that we hash something very special. I know everybody knows that phrase, and we didn't put any trapdoor inside. There's actually many hash, in symmetric encryption and hash and digital signature. There's some parameters, and in the specification, the white paper, they will show you that okay, the initial parameter actually from some famous phrase to make sure that okay, nothing on my sleeves. So it's here in the transient setup is same. Okay, this string is very, very important. Okay, here, yeah, it's very important for you to implement. Please remember that. It's dangerous too. Okay, I think as a homework, you can prove that the knowledge sound is an extractor for this protocol. Okay, as a homework. We can discuss that in our DC channel. Okay. Binding, hiding. Oh, okay. As another problem, another point. I should mention that. Okay. Okay. When we're talking about hiding and binding, okay, this commitment is a very important, very simple commitment. It also has the hiding and binding, but the differences are that here we just use square bracket. Let's define the square bracket r equals to gr. Okay. This commitment is strongly binding. Strongly binding. But here it's not strongly binding. That's why we have such attack. This is not strong binding. But it has stronger hiding property. It looks like two sides of You cannot get both. It's a trade-off. Either you have privacy, or you have stronger soundness. So for Peter commitment, we have perfect hiding and computationally binding. What do you mean by computationally binding? Put it here. Perfect hiding and computationally binding. So perfect hiding saying that, okay, we don't worry about any verifier. If in the future, for example, 100 years later, then everybody can use quantum computer. So they cannot decrypt the key from the commitment, right? Even after 100 years. So that's the reason why I should put the Peter commitment on chain instead of this one. But the computational binding, actually, we assume the prover has limited computation resources. Otherwise, the prover can, to compute that, okay, the relationship between G and H, to get a result of U. If prover has unlimited computational resources, the prover will get U. So that's why we call it the Peter commitments has the computational binding. So it's a security assumption that prover, is nowadays computers, not 100 years later. Okay. But this commitment is a simpler, is stronger binding and computationally hiding, as you can see. So the bad news is that we cannot get them both. Perfect hiding plus perfect binding. Okay, we cannot get that. We can prove that. That scheme does not exist at all. We cannot get the perfect, everything perfect protocol. We have to trade off. We have to do some trade off. So the two different type of commitments are close to a relationship between proof and arguments. So in zero-knowledge proof, when we talk about zero-knowledge proofs, nowadays the proofs actually are arguments. Arguments in that, okay, the commitments are computationally binding and perfect hiding. So this is argument. So argument is more useful in crypto. Because the argument, so only arguments, we can compress a huge witness, huge private state into very short proof. Just because we use the Pearson community, like, the family who have the perfect hiding and the computational binding, they can use arguments. So that the reason we can compress a huge computation traces into just just 1 or 2 kilobytes long proof. Okay, but today we don't go too deep into it. I think probably in the future we can if we learn more the concepts, we can discuss it. It's a very interesting. Okay, wow, it's a 1 hour and 20 minutes. Okay, so I think it's almost over today. And in the last part, I will show some code and I wrote in this weekend. And I encourage everybody to just contribute to the code base, and you can try the very basic product design to get the basic skills or experiences. It's quite fun. Okay. Okay, thank you. Yes, let me use that. Okay, so far, any question? Why so quiet? I hope everyone can follow, because we'll go up gradually. sorry. Wait a minute. Okay, here's my time.
Mr. Wu, the trapdoor and hash to point is the same thing?
Trapdoor and
And hash to point is the same thing?
okay. They are related. Okay, they are related. Yeah. Yes. Yes. If you use hash to point to calculate age, we don't have to know u. We just directly pick using hash to randomly pick point from an elliptic curve. Okay, we have two ways to get an elliptic curve point. The one is that every point on curve, you will have a u that we can calculate age from the generator of the elliptic curve point, because all elliptic curve points forms a group, a cyclical group. So G is the generator of the elliptic curve point set. So every point can be something like that, the relationship. The second approach that because the elliptic curve has x, y coordinates, right? We use hash function to get a x, and then we calculate the y, because x, y satisfy the elliptic curve elliptic curve formula. So we calculate y. We get x, y to test if x, y is in the group. If not, we just slightly increase x and test x, y. If not, we just and then we add small piece of value on the x get to test. We just try and fail. Try and fail. So repeatedly try to get a point in the group. Okay. The second approach that we ignore that u, if u exists or not, or what u is. So then we have a transparent setup, and nobody knows the. Yeah, we don't have u. Yeah, you can Google hash point. I think that Wikipedia will have some articles about that. Sorry.
I'm asking because
Sorry?
I see something that like this the same thing, yeah? That's why I asked.
Okay.
I asked it because I'm seeing things here that it's like I'm using the AI to do some, yeah?
Okay, yeah, okay.
And in AI they use the same
same
notation for the two. It's not okay, yeah?
Yeah,
I think it's not right, huh? Or it's right. I don't know.
I think it's okay. Yes, I think it's cool. Yes, it's correct. Almost correct, yeah.
And trapdoor?
Yeah, trapdoor function is a different concept.
Okay, but is not right?
Not right.
Not right.
Trapdoor function, yeah.
So actually, we don't want people to find out what is you. That's the reason we use hash.
Yeah.
Okay.
Nobody knows that.
Okay, trapdoor is not right.
Okay, all right. Okay. I think. All right. Okay, here is a mini course on PCS in Python. So there's just a very simple code that related to our mini course. I'm still a Python beginner, so I hope to learn from you. For example, here is a simple Schnorr protocol. Yeah, we have the stronger binding commitment code. Look like it's very simple, right? And there's a class of prover has two functions, three functions: the constructor and the round one. Sorry, let me. Is it okay? It's clear. The prover has the constructor round one, round three, right? The class of verifier has a constructor round two in the verification step. And then we have a run Schnorr, this short script, to create a prover and create a verifier, then invoke the round one function on prover, and just put the result of generated by the prover and pass it to the verifier round two. Okay, it looks simple, right? It looks very simple. Okay, then return the verifier dot verify function, which returns a boolean to indicate whether the prover is passed or not, is accepted or not. And then we have a simulate function to prove the knowledge soundness of Schnorr protocol. So I will not explain those code here because it's a tedious, and I think just look at it after the course. And also we can build the extractor. So now we don't use the the paper the approach to prove the security. Actually, we can write code to prove the security. Okay, it's a simple Schnorr. We will have more and more protocols that we will talk about here. We already put some, probably some for next session. Next session probably tomorrow or the day after tomorrow. I will discuss with Hood. Yeah. And I think it's a way to do some experiments. I think in this week we will finish with a very simple minimal polynomial commitment scheme, which is simple, very easy to understand, but it's not practical to use. Then we will next week probably we will. All right. I think this Friday or Tuesday we will to go to the KZG10, the polynomial commitments, and then next week we can build some protocols above that, okay, above the polynomial commitments, and eventually probably we can have a small proving system that with many state-of-the-art features, even it's very small to understand. So we still have 5 weeks to. Yeah, but it's a long journey. We will go up quickly. So, yeah, I hope all of you guys can enjoy that using Python to explore more things. Yeah. Okay, that's all. Okay, thank you for coming. Thank you for coming. Yeah, we have the Discord channel, ZK Collab. Yeah, I think probably we can discuss some stuff there. Yeah. Thank you very much. Thank you.